Here we are in cluster 3. We're ready to start talking about systems of linear equations, inequalities, and absolute value functions. The majority of this cluster is going to be on this first objective, systems of linear equations. Inequalities and absolute value functions will be some minor details tacked on towards the end of the cluster. All right, so beginning in section 111, we're looking at systems of linear equations in two variables. And we know that a single linear equation in two variables forms a line shape. A system of linear equations is going to involve two linear equations. So we're going to be looking at intersection points between two equations for these systems. Two linear equations that have two variables each. That's what a 2 by 2 system is. 2 by 2 system means two equations and two variables. So we're going to solve these numerically and graphically. So with a table and a graph, we're also going to solve them by hand using the substitution method in this section. And then solving a single variable equation using the graphical method with two variables as well, ancillary. All right, so in our first situation, we are moving back home for the summer and we need to rent a truck. So there are two companies. One charges us $60 per day plus 75 cents per mile. The other one charges us $30 per day plus $1 per mile. So I need to identify the input and output for this situation. In our situation, the total cost of the rental truck for one day is a function of the number of miles. So total cost is a function of the number of miles. So in this, I can read directly. It's a function of the number of miles. So miles must be the input, number of miles. And then the output has got to be the total cost. Okay, so we're going to let N be the total number of miles driven in one day, and C is going to be the total cost. We're going to write an equation for truck 1. All right, so the output's the total cost of truck 1. So truck 1, the cost is going to be defined by it costs $60 per day, plus it costs 75 cents per mile, and 75 cents per mile is 75 cents times the number of miles. So what they're actually telling me up here, this is a linear function. This is my vertical intercept. This is my initial value. And this is the rate of change, the amount of increase per mile. Rate of changes always have per in them in the middle of the units. Between dollars and miles, we have that per, signifying that's the slope or rate of change. Now, this is per day, so it does have that per in it as well. However, since we're looking at just one day, we can ignore per day because it's per singular day, and so we don't have to worry about that. If we had multiple days, this would involve an additional variable, but in this case, it does not since it's one day only. And in the second company, the cost here is $30 per day plus $1 per mile. Okay, so we want to complete this table and we're going to autofill these functions. So just so that I can make these autofill when I get to Desmos, I'm going to rename this first one as f of n, and I'm going to rename this second one as g of n. I can't have them both be f of n because I could not get both of them to autofill if they had the same name. So let's give them different names. Okay, opening my Desmos too large over here. I'm going to type those two functions in real quick. We've got our f of n is 60 plus 0.75n, and our g of n is 30 plus 1n. All right, making ourselves a table here so we can autofill. I'm going to pull the screen over to the side for a moment. We want to plug in 0, 20, 40, 60, and so on. So let me start typing those values. They should autofill if I just hit enter enough times. And I'm going to expand this part of it. I have those two functions I want to plug in. One of them is the function named f, plugging x1s in for the inputs. The other one's the function named g, putting x1 in for the inputs. So if you just go over, you can insert additional columns to your table. If I hit the arrow key to move over on my keyboard, that's how I was able to enter 3 columns into this table, and I can fill in for multiple functions. I only have those 2 functions, so I don't need a 4th column. So let me, I might be able to pull this up high enough that I can see these numbers and write them down here. All right, so we have for company 1, at 0 miles, we have $60, 20 miles, $75, then 90, 105, 120, etc. I don't need to read these. I know you can see them on the screen there as well. I need to scroll down just a teeny bit to get the 160. So that's 180. And for the other company, okay, so almost done. Got to scroll down, and our 160, we are at 190. Okay. For what mileage, our next question asks down here, for what mileage is the 1-day rental cost the same? So if I compare these, 60, 75, 90, etc., what day are they the same? So they're not the same until I get here. So at 120 miles, they have the same cost. So for what mileage? It would be for 120 miles. They have the same cost. At $150. What company should we choose if we intend to drive less than 120 miles? If we're driving less than 120 miles, we should choose, so these values are higher, so I would want to choose company 2 because company 2 costs less in each of these rows before the 120 miles. But if we're going to drive more than 120 miles, then company 1 has the lower outputs. So if we're going to drive more than 120 miles, we'd want to go with company number 1. Okay, so graph the two cost functions. So I'm going to just move my decimal screen back into prominence here. And I'm going to click on the magnifier glass so I can see my functions. All right, I'm going to shorten this over here a little bit so I can see my function. And if I give one of these lines a click, I should see this gray dot appears here as the intersection point. Again, the gray dots that appear are points of interest, and the intersection points, the point of interest, you also have your intercepts being gray as points of interest, but we right now would wish to consider the intersection point to be our point of interest. So if I look at my graph, I can see the intersection point at a 120, 150, and that's what we're asking right here in B. If I determine the point where we intersect, that's at the point 120, 150. And just a quick sketch of our lines. We had 2 lines, and we're looking at the intersection point right there. Just by clicking on it, we got a 120, 150. What is the significance of this point? Okay, so this means that after or at, I should say, at 120 miles instead of after, just right at 120 miles, both companies cost $150. Emphasis on the both there because that's what that means, that they are intersecting. Both companies cost the same amount. They both cost $150. Intersecting there, they both have the same output for that input value. Okay. Definitions down here at the bottom. It says that if you have your 2x2 system of linear equations, that just means you're looking at 2 linear equations together. We had 2 linear equations we looked at together. It doesn't matter what the A and B and C and D is, just slope of the first, slope of the second, intercept of the first, intercept of the second. The solution to the system is an ordered pair that makes both of the equations true. If there's exactly one solution, the system is called consistent. So your consistent solutions are going to be places, graphs where there is one solution. If you have 2 variables, You can't have more than one solution, but as we'll see in a little bit, it's possible that the lines might be parallel, so they don't cross, they have no solutions, but the maximum number of solutions is one. There's no way that a straight line could cross again, so one solution is the most that it could have for distinct lines. All right. Okay, so next page, we have our system in the truck rental situation. So again, we could write it as a system. This curly brace I'm drawing on the side just groups together your system of equations. We first solved it numerically. We solved it numerically when we were completing this table and identifying numerically where we had the same output. Secondly, we solved it graphically when we were looking at the Desmos graph and finding the intersection point. Each of those has its own pro and cons. Numerically, you could easily miss the solution. If, for example, this had counted by 50s and went 50, 100, 150, and 120 just wasn't on the list, I could have easily missed this. Or if the answer had been at 99 and it wasn't on the list, I could have missed it. So numerically has some disadvantages based on what you choose for input. You might get lucky and see the outputs match up, or you might not get lucky and see the outputs match up. Graphical has some advantages that you're able to just see where they cross, but if you have a problem getting your scaling correct, figuring out in what window to view this, you might have some issues finding it graphically. And perhaps you need more decimal places than you can find graphically, since graphically is always going to round to 3 places. If you need any more precision, you may have to do it by hand, and we're going to look at the substitution method for this. There's a nice example through this page. I'm going to get to the one for this question, and we're going to use the substitution method to solve our truck problem. So it was C equals 60 plus 0.75 n, and C equals 30 plus 1 n. All right. So the idea for substitution is that since these need to be equal, this C and this C need to be equal. So if C is equal to 60 plus 0.75 n, then that can go here in place of C, since the C's are equal to each other where we intersect. So we're going to make that replacement, and right here, in place of this bottom C, we're going to put in the 60 plus 0.075 n equal to the 30 plus 1.00 n. That's called the substitution step, where I substitute the value of C in place of C in the other function. So we've substituted 60 plus 0.75 n in for C. Now we solve like we would usually solve an equation like this. So we would, I would subtract the 0.75 n from both sides to get the n's all together. So that would give us 60 equals 30 plus 0.25 n. I would subtract 30 from both sides. So I'm going to write it right underneath here, and then I'll put the work on the top over there. So if I subtract 30 from both sides, 60 minus 30 is 30, equals our 0.25 n, and then I would divide both sides by 0.25, and that gives us 120. Okay, so what does that value of n represent? N is the number of miles. So the equations intersect at 120 miles. All right, now I only have half of the answer right here because I only have the 120. So to finish this question, I need to take my 120 and plug it into the equation for n and solve for the C value. It does not matter which equation I choose. If I choose to plug it in for n in the top equation or the bottom equation, it does not matter. I will get the same answer because both of them are going to equal the same thing. I'm going to use the bottom one just because I can do 1 times 120 in my head. I don't have to worry about 0.75 times 120 and getting in my calculator. So in the bottom one, C is equal to 30 plus 1 times 120, and that's 30 plus 120, which I know is 150. check to see it satisfies both equations. So they actually want me to prove it in the top one. All right, so we'll do that. I have my 60 plus 0.75 times 120. Let's make sure that we do get our 50. 60 plus 0.75 times 120. 150. All right. So we can see that we get the same thing, and this is the cost. So once again, by hand, we were able to see that, yeah, we get $150 no matter which company we use if we're driving 120 miles. Okay, so the next example looks like a new situation. We are going to graduate and we're going to buy a new car. We've narrowed it down to an Accord or a Passat. And we're concerned about the value depreciating over time. We search the internet and we find the following information. Suggested retail price and the depreciation. So the suggested retail price is going to be our initial value. That's our B. Our depreciation rate is the growth change per year. That's going to be our slope. Okay, so I'm going to complete this table. And now, technically, I could complete this table without writing an equation, and I will do that for the first couple. Maybe I'll do that for the Accord. So for the Accord, I know that initially it starts at 23,130, and I know that if I want to find the value next year, I can subtract the rate. Let me open up a new graph right here. There we go. Just in case I need to come back to that previous example, I'm going to keep it open. And we are taking our 23,130 and we're subtracting our 1385. And so this value is 21,745. So sure, I could do that again. I could subtract again. But I like to use Desmos to autofill tables, and since I'm going to have to write the equations anyway, let's just go over here on the next page, and we'll write those equations, and we'll come back and we'll do the autofill table, because I think it's more fun. All right, so we're going to let V be the value. We want to write the equation for the Accord, and we want to write the equation for the Passat. So Accord. So we'll do V equals. So the value is 23,130, and then we're going to subtract 1,385 each year, and our years are probably T. Oh, actually, it's X. Okay, so we're going to use X for the number of years. That's what they've asked us to do. And then for the Passat, it's still V for the value, and the initial value here was 26,370, and we're going to depreciate by 1,790 per year. Now that we have our two equations, we can get those entered as functions. If we're going to make them functions, I'm going to call this one f of x and this one g of x. And that's going to allow me to do the table with the autofill stuff again. So let's do that. I need to type my two equations first. So f of x for our Accord, 23,130 minus 1,385, and g of x 26,370 minus 17,790. There we go. X. Table. And we need inputs of 0, 1, 2, 3, and 4, and we need outputs f of x1 and g of x1. And I will make this larger, move it over here, and then I'm going to go back in our book to finish the table. Okay, so I'm going to pull that Desmos up a tiny bit higher. So like we noted before, I can do this by hand, just subtracting, but it's faster this way to get the values for the other years. So 20,360 and so on. for our accord. And then over here for the Passat, same thing. We can see our 26,370, which was our initial value, and we're depreciating at 1790 per year. Okay. So we're asked down below, will the value of the Passat ever be lower than the value of the Accord? Okay. So the value of the Passat is higher. Still higher, it's still higher, it's still higher, it's still higher. Originally, it's 3,000 and change higher. 3,000 and change higher. 2,000 and change higher. Still 2,000 and change higher. We're under 2,000, down to like 1,000 and change higher, right? So it's higher still, but it's not as high. And the Passat is losing value a little more quickly because it has a higher value for slope. So yeah, because it's losing value more quickly. Oops. So it's got that higher negative slope, losing value more quickly. I just don't know when yet, and I don't know how far to make this table. So I could just keep punching in values and see if I can find it, or as we are directed, we could go ahead and solve this system by hand, and that's what we're going to do next. All right. So I already have the two equations written up here, so I'm not going to rewrite them right away in this space down here. I'm going to instead say V, which is equal to 23,130 minus 1,385, is going to be plugged in place of the V, the value in the second equation. So we're going to write that directly down here. So 23,130 minus 1,385x equals, that's right here in for V, equals 26,370 minus 1,790x. Now we solve. So I need to get my variables on the same side. I'm going to go ahead, since that one has the larger negative number, I'm going to add it to both sides. So I'm going to add 1,790x over. I can use Desmos to assist with the calculation. I need to take 1,385 plus 1,790, and I can see that I get 405. So I will have 23,130 plus 405x equals 26,370. And continuing, trying to get x by itself, got to get rid of this constant, move it to the other side. So we're going to subtract the 23,130. So our 405x move by itself, and we will have 3,240 when we finish that subtraction. And then continuing to get x by itself, that's multiplication by 405, so we will do the opposite and divide both sides by 405. I'm going to use Desmos to help with that calculation again. Okay, so I need to take 3,240, and I needed to divide it by 405, and I get 8. Cool. Okay. All right. So I'm not done solving yet. If I know that x is equal to 8, that's half of my solution. Remember on the other side when we found our n value, we still had to go back and find our c value. So I'm going to do the other part. I'm out of space. I'm going to do it in the margin up here. But now that I know that x is 8, I'm going to take 8 and plug it into my function for x. I can choose either one of these functions. It doesn't really matter which one. So I'll just go for the top function here. So over here on the side, our value is going to be 23,130 minus 13,000 or 1,300 85 times 8. And I just have my decimals up here still so I can use it to help me with that calculation. So 23,130 minus 1,385 times 8. I got 12,050. And so had I plugged the 8 into the other equation, the Passat equation, the value should have been identical. So the solution here is, I'm going to write in my sentence, so after 8 years, let me get rid of that decimals graph for a second. No, I'm going to keep it because I need it for part E. After 8 years, the value of both cars is $12,050. All right, now E, you solve the system graphically. How does my solution compare with what I did by hand? I can't see anything. My equations are in there. Luckily, I already have a table started, so I can use that to get into a good window. So I'm going to zoom. And then I still have to pull it a little bit because 8 wasn't in the table. But I can see 8, 12,050. That matches exactly with what we had got when we solved this using the substitution method. Perfect. Had I also continued in my table beyond 4, I need to make this a little bigger to verify. I could have seen that these were going to match up here where they had the same output. Tables, though, aren't usually my preferred method because you don't really know until you know the answer how far you got to go in that table to find out whether they're the same. And you also don't know that it could have happened at 7.5. I don't know that I had the correct increment to do this in the first place. So tables are last choice in this option. But the graph, once we can see the lines, we can find where their intersection is. I'm going to turn off the dots for the table here and just look at the two equations and see their intersection point there. All right, so how does your solution graphically compare with what we got by hand? We have the same solution. So graphically, we also have that same ordered pair, 8, 12,050. The solution to the system is an ordered pair of the form x, v. What do the values represent? All right, so I already wrote my explanation over here, so just draw an arrow. It means after 8 years, the value of both cars is $12,050. Which car has the better resale value? Well, it's going to depend, right? So if it's between 0 and 8 years or before 8 years, then it's the Passat, right? Because the values were all higher in the table before 8 years in the Passat's column. But then after 8 years, then the Passat's values are lower. Then it's going to be the Accord. So it's not a straight answer about which one is better. It really depends on how old the car is. If you're going to sell it before 8 years, the Passat is the better resale. But if you're going to sell it after you've had it for 8 years, you would want to sell the Accord. Okay. Next, we've got another situation at the bottom with number 7. You and your friend are traveling in the same direction but in different cars on the New York State Thruway. D is the distance you are from your common starting point. And we're traveling at 65 miles per hour. So our distance would be 65 times our time. Multiply your speed by your time, you'll get the distance you've traveled. So 1 hour, 65 miles, 2 hours, 130 miles, and so on. Write another equation to determine the distance that your friend is from the starting point. She's traveling at 60 miles per hour. We were at 65, but she's got a 30-mile head start. So we're going to give her that 30-mile head start. She had already gone 30 miles, and then she's going to travel at 60 miles per hour. So those would be the two equations we're going to start with. Okay. Just in case we couldn't get them, the book went ahead and recapped those two equations for us down here. But we can develop those equations because we've got the skills. We know what our rate was, our speed was. There was no head start here, so we didn't have initial value. The head start came as our initial value there. Okay, So what do we get to do with that? I get to make a table. So I better open my decimals again. Just going to clear this one and we'll put in our two equations. So I'm going to call my distance f of t. I didn't mean to capitalize that f. There we go. And we were at 65t. And then we'll give my friend the function g. And she had a 30-mile head start, but she drives slower. There we go. Okay. And we want to make a table for f at x1 and g at x1. And we want 0, 1, 2, 3, 4, 5, and 6. Okay, so let's fill these in on our chart here. I should just pause while I'm writing, but I'm sure you're writing as well, so I'll keep it rolling so you don't have to pause. We've got most of these filled out for our distance. All right. Now, it says solve the system using each of the methods. Solve the system numerically. Solve the system graphically. Solve the system algebraically. So can I see it numerically? Do I see a spot where they're the same? Oh, thankfully I do right here at the end. Had I not gone to 6, I wouldn't have seen it. But right here at the end, I can tell that the solution is 6, 390. So I can interpret that right away. We'll solve it, the other two methods, in a moment, but I can do the interpretation for part B for this right away. 6, 390 means that after 6 hours, we meet up. Meet up means we intersect, but people, you don't say we intersect, we meet up at 390 miles from home. Maybe you got a rest stop there. Maybe you reach destination. But after 6 hours, you met up 390 miles from home. Okay, now we're going to solve that same system graphically. So I'm going to move my decimals back over here. I can use the zoom fit to help me find it, but I'm going to pretend I hadn't done this numerically, so I'm just going to delete my table. And I want to have to experience how to find it if my table wasn't there. The zoom fit would help me get there faster. I thought I X'd you, table. Go away. Okay. So zooming out's not going to help because the numbers were so big. We know the answer is 390. So I'm going to manually rescale this. If I didn't know what it was, I would just start jumping it up higher and see how 100 looked. I was like, nope, 100. They don't look like they're going to cross. 200? Sort of. 300? Oh, I see they're getting really close up there. I'm seeing right here they're getting close. Maybe I'm just going to jump to 500 and be done with it. And if I click on one of the lines, I can't see exactly where they cross, but I click on one of the lines, don't forget that gray dot, which is a point of interest, intersection point, is going to show up. So I know they cross at 6, 390. All right. So again, if I wanted to see it a little better, I could shrink my x-axis down. It's going up to 22. If I cut it down to 10, perhaps, then there's a little more space between the lines. I might be able to pinpoint where it was. But again, the gray dot showing up is of great help. So I can see my two lines are very close together, but I'm able to identify where they cross. So I'm going to draw it like this, and we're going to pinpoint our intersection point at that 6, 390. Okay, so algebraically, my equations were d equals 65t and d equals 30 plus 60t. Algebraically, I know that when D is equal to 65T, 65T is going to be plugged into D in the other equation. You could do vice versa, of course. You could put this stuff in that equation. It doesn't matter which order you do this. You just pick one of the equations and you plug it into the other. Okay, and I got to get my T's on the same side. I'm going to move this 60T to the left just because there's only T's on the left, so I might as well gather them all there. So that gives me 5. T equals 30, and I know if I divide by 5, I get T equals 6. Half done, more than half. But now that I know what T equals 6, I have to plug that back in for T to find the D value. Doesn't matter which equation. So I'm going to use the top one because I want to. I guess there's just one multiplication in it. And I wouldn't necessarily know what 65 times 6 was off of the top of my head, so I might go into, I pushed the wrong button, there we go. I might go into, let me get the other one back up, Desmos, and just ask what 65 times 60 is. I meant to say 65 times 6, and I get 390. So I get my D equals 390, so I misspoke there, but D equals 390. Okay, so again, just comparing all 3 methods of numerically, graphically, and algebraically. Same answer here. We got our answer, and we got our answer here with our T and D values. All of them have the same interpretation. Okay, so again, this system is consistent like we defined earlier because there's a singular solution. Exactly one solution. Now, number 9, do all systems have exactly one solution? Let's find out. The answer is going to be no. So you and your friend are traveling again. She still has a 30 mile per hour head start, but this time we're both going to go 60 miles per hour. Will you catch up to your friend? So she's 30 miles ahead of me, and we're both going at 60 miles per hour. So she's going to go at the same rate I'm going to go. I'm never going to catch her. I'm going to get to where she used to be. I'm never going to catch her. So no, I can't catch up if I'm not going faster than her. We're going the same speed, so we won't catch up. Okay, so this situation can be represented by 60 t plus 30 and 60 t. Both of our speeds are 60. She's got a 30 mile head start. Try to solve this system graphically. Okay. I'm just going to change this equation here to 60 t, and so those match. So I don't see the intersection anymore, and what I should notice is that those lines are parallel. They're not narrowing in towards one another. They're parallel. They're never gonna cross. So when I observe them graphically, I better know they're parallel because I can see that they have the same slope, and that's the definition of parallel, but I can also see that visually there. So they do not intersect. So these are parallel. They do not intersect. What is the solution to the system? There is no solution. Remember, a solution is going to be an intersection, so if they don't intersect, there is no solution. Try to solve this algebraically. Okay, at the bottom of my page here, so it's a little awkward to write. If I try to solve this algebraically, again, we're going to take what D is equal to, plug it in for D. So that gives me 60t plus 30 equals 60t. Now, we want to move this 60t from the left to the right because there's only t's in that side. We might as well get all our t's in the same side. When I attempt this, I get 30 equals 60t minus 60t is 0. It's not 0t even. It's just 0 because there's no t's left at all, so it's 0. And 30 equal to 0 is a false statement. And so this implies that the answer is no solution. I have to push down on my book to be able to write on it at this angle. So sorry, my hand being all over the place there. But there's no solution. And so this is how no solution would look if you were doing it algebraically, you would see a false statement, something that is not true, leading you to the conclusion that there is no solution. You can see it graphically because you can see that they're parallel, they're not going to cross, so you can see that there's no solution. Okay, so on to the next page. When this happens, the system is called inconsistent because the lines never intersect and it results in a false statement. So if it's inconsistent, there is no solution. One more scenario here. Now me and my friend are taking another trip. This time, she does not have a head start. We both leave at the same time from my house in the same direction. We both travel at 60 miles per hour. When will you both be at the same point? So, we're leaving at the same time. We are heading in the same direction. She's probably in my passenger seat. When are we at the same point? Always, right? Always. Because we left at the same time, we went at the same speed, we're always in the same spot. You got to be in the same car for that to happen. Otherwise, I mean, if not in the same car, she's got at least a 2-second head start. She's got to be in your car. You're always in the same spot. You're always in the same, you must be in the same vehicle. So always. And so this would be our setup. We both have the same speed, 60t. There's no head start. Try to solve the system graphically. Okay. All right, so let's just take off our head start. Okay, I see g of t. Where's f of t? If they are the same thing, right? If I turn g of t off, f of t is right underneath it. Or if I make g of t dotted, I can see the dotted line on top of the solid line. So I should be seeing that both of my lines are in the same spot. The dotted line is on the solid line. They're the same thing. They are the same thing, showing that they're always, always intersecting. For every point on G, they are intersecting. So the lines are identical. Do the lines intersect? Yes, all the time because they're identical. So yes, they are identical lines. So what is the solution to this system? Well, since they're intersecting all the time, every point on the line is the solution. So there are infinitely many solutions. There's not just one. So we can say there are infinitely many solutions, and every point on d equals 60t is a solution. Okay, every point on the equation is a solution. Try to solve this system algebraically. Okay, so again, what I know that d is equal to in one equation goes in for d in the other equation. So 60t equals 60t. And I got to get my t's in the same side. So I'm going to subtract 60t from both sides. And that gives us 60t minus 60t is 0 equals 0. This time, this is true. I mean, 0 is equal to 0. And that's the difference between this case and the last case. 0 equals 30 in the last case was not true, but 0 equals 0 is true. So this means that there are infinitely many solutions. That's how many solutions there are, but what are the solutions? Or every point on the line is a solution. So every point on D equals 60t is a solution. And when this happens, the system is called dependent. Graphically, they are the same line. The system has infinitely many solutions. When you solve this, the answer is that the equation is true for all t on the line. So the equation itself becomes the solution.